A pull up or pull down resistor simply sets a default voltage level on this line when it is floating. Another word for floating is high impedance or high Z. So that just means that nothing is actively sourcing or sinking current onto this line. So it's effectively doing nothing. This is actually really bad because a floating line is just hanging out like an antenna. So EMI noise will go on this line, and because it is high impedance, it does not take a lot of current at all before this input causes this output to change to something that you did not intend. So you should always know what your circuit is doing at all times. And when you have floating lines, that is not the case, which is really bad. So what can make a line floating is, this could just be how the pin itself is configured. That can be fixed, but there's also a couple of other scenarios. So in your microcontroller, if your reset pin goes active, that means all the pins go high impedance. So you're going to need these anyways. Another scenario is what is happening to the pins is when this thing is being programmed, if it is being programmed in circuit. So look at your data sheet for that one, but when it's being programmed, it could also make these lines go high impedance. So we don't want to cause undesirable behavior when it's programming. So, okay. So we're going to switch to simulation now. So it's going to get a little busy. I'm showing you exactly what you see on the screen here, just with parasitics and some setup. So let's get this out of there and zoom in a little bit so we can explain this. Here's our 3.3 going to our pull-up resistor right here. Every pin will have a little bit of leakage. I looked this up for microcontroller. Maximum 1 microamp is what it said. Every pin's going to have a little bit of capacitance here. And then this stuff right here is just how I'm getting the pin to drive the trace low. Then on the other side, we're also going to have some leakage. We're also going to have some capacitance. What I'm also going to show you is that we have some trace to plane capacitance here. So let's talk about that for a second. Saturn PCB Designer. I simply set a trace width 10 mils, conductor height, this height here between trace and plane, also the 10 mils, that's consistent with the 4-layer board. And then I said 10 picofarads, that's going to be about 4 inches. So not kind of a long trace, but not unheard of at all. So that might even be short if you have a large board. So anyways, let's do it. We're going to do VCC here. Then we're going to do the trace that is being pulled up. So the way I have this set up is we have the line starting out high. The microcontroller will make this signal go low for 5 microseconds. Then after that, the pin is floating, and then it's up to the pull-up resistor to get this voltage back up to where it needs to be. Just another thing we're just going to show real quick is the current through this resistor. I mean, it's just 3.3 divided by 10K, so we get our 330 microamps. So nothing special there. But I do want you to give a little bit of thought for a second. What if I have 10 pins and 10 pull-ups or pull-downs? I mean, this turns into significant current if you are battery powered. If you're not battery powered, then you might say, who cares? So, but if you're battery powered, this turns into a big deal real quick. So for that reason, if you're battery powered, go to 100K. So we see a few things going on here. First of all, this is R, these are C. We've got an RC time constant going on here. So you need to look in timing for your circuit, see if this kind of thing is acceptable. Another thing you might see is this voltage maxes out a lot lower than our 3.3 volt. Like this is over 10%. So we've got, that's just because for our leakage here, 2 microamps going on here times 100K equals whatever this is. So since we are talking about digital signals, this is okay, but it is something you need to be aware of, especially if you're going to try to go much higher. So obviously, if you need to go higher, you need to know more about what you're connected to. Like I really need to know this leakage and capacitance. Yeah. So let's go fix this. We have a few levers we can fix, but not many. So one is just make the darn thing shorter. If we do that, obviously that's going to change. That's going to make this look a lot better. So if this is crazy too much, it may not have enough time to get high before your circuit's doing whatever. Okay, on the leakage front, there's not much you can do about the pins, but what I will occasionally see is, say, like a TVS diode or a Zener. So I just want to go into this real quick because this has its own set of leakage and capacitance, and it can be a big deal. I have seen this break circuits. So if we go into this TVS diode here, we go down the data sheet. So this one's big, physically big. I can do 600 watts. So this first one here in the list is 5 volt, but look at its reverse current, maximum 800 microamps. I can tell you in the real world, it's not going to be anywhere near that high, but you got to go by the data sheet because that's just smart. So that's crazy compared, like, can't do that. Not acceptable. And then if you also go down here, we see the capacitance here. We're at over 1,000 picofarads. This thing will absolutely dominate compared to everything else. So you don't want to do something like that. But there are others that you can get. So this little thing here is meant for 3.3 volt, 2.5 picofarad, leakage current, 0.1 microamp. Much, much better. It'll still contribute. So if you need it, you got to have it. So with those high value resistors, you got to account for this. So we have that. So everything I'm showing you is pretty much the opposite if you did a pull down resistor. I'm just doing a pull up because it was easier for me. So this thing's not going to have a TVS diode in there. So let's go back to, because of this, I want to go back and kind of sort of tell you what to do for layout. So I have actually seen, here, let's go ahead and edit this. I'm going to show you what I've seen in real life. 100K. And then this thing was stretched out big time. And then this was put, oh, good Lord. I have seen a layout similar to this. How do I know? Because the darn thing didn't work. And it didn't work because of all this trace capacitance here. Or so I'm led to believe. I didn't actually measure it. In the real world, at my job, I am a busy man. I cannot turn everything into a huge research project. But I saw basically this for the layout. I'm like, all right, well, I don't want to do a layout change. So what's my only option? Take that, we lower it to 10K. So there you have it. A little bit of an intro on pull up resistors. Remember, pull down is basically the same thing, just in reverse. So if you want me to go deeper on this or you have questions, let me know. I'm more than happy to answer them. So thank you for your time. Goodbye.